In this situation, I've got a man pushing a couple of different boxes, okay? They each weigh 150 pounds. Basically, the question becomes, how hard does that guy have to push until motion occurs? And really, the question also becomes, well, what kind of motion is it when that happens? So what we'll do is we'll break this actually up into two free body diagrams, okay? Box one, and then box two, like so. And box one, again, I'm pushing on it with P as shown here. This box has a weight of 150. Okay. And then, of course, if I've got P heading in that direction, I've got a friction force here. I'm going to call this friction force 1. Okay. And then similarly, I'm creating that couple between the friction and the applied force. So my normal force is going to shift over. I'll call that normal force 1. Okay. And it's going to shift over some amount that I will call X1. Okay. I'm going to give myself a little bit more space here to draw the top guy. I'm sorry, the bottom guy. Okay, so that's the free body diagram on this one. Now, drawing the other one, Newton's third law tells me N1 acts straight down. Okay, friction goes in the other direction. Okay, what a lot of people will do is they'll make the assumption too quickly that that normal force is the weight, and they'll think, oh, well, the weight's pushing down, which is true, but it's a better idea to think of it as a normal force that's been shifted some amount x1 with the friction force applied to it as well. Okay, this guy also has a weight of 150 pounds. Again, pounds are the force, so I don't need to worry about dealing with that. And then I'll have a second friction on the floor, F2, and a corresponding N2, which will be at some distance x2 over like that. So those are my free body diagrams. Okay, so what I'm going to do now is I'm going to sum my forces in the, basically apply my equilibrium equation. I'm going to get 6 of these, right? 3 for each body. Okay, so on the first one I have P, I have F1, and I set that equal to 0. Okay, then I've got the sum of the forces in the x direction. I've got N1 minus 150 equals 0. Then I've got my moments, okay? Again, I do it about the point right below the weight there. That gets rid of both my friction as well as the 150 pounds. And I only have x1, n1. And then it'll be 0.5 times p equals 0. So those are my first 3 equations for the equilibrium of the top object. Now for the bottom object, I'm going to have the sum of the forces in the x direction. And on this one, I have F1, I have minus F2. Scroll down just a little bit so you can see what we're doing. And I'll set that equal to 0. Sum my forces in the y direction. I'm going to have N2, I'm going to have N1, and then I'm going to have the 150. N1 and 150 are both going down, N2 is going up. Okay, and then I'll sum the moments about, again, the point right below the 150 right in the center there. That gets rid of the 150 as well as the F2. Okay, now this time I'm going to have a couple of n, or I should say moments due to n. I'll have x2, n2, and then I'll have negative x1, n1. Okay, and then I've got the friction force up at the top creating a moment as well. So that's going to be negative 4.5 feet, the height of the box, times F1. Of course, F2 goes right through the point, so I don't worry about that. And I set that equal to 0. Now, what I want to do is I want to kind of set aside these equations. These equations above this line, these pertain to everything. Regardless of how the motion occurs, these equations hold true, okay? Regardless of what's going on with friction. So let's go through and talk about a few things. From this equation, I learned that P equals F1. From this equation, I learned N1 equals 150, okay? Yeah, I can minimize this one a little bit. This is going to boil down to 150 x1, and that's going to equal 0.5p. That's just kind of plugging in what I know about N1 right? And simplifying it a little bit, okay? From this guy, I learned that F1 equals F2, and of course, that means that also equals P from this equation up here. So however you want to think about it, now I know P, F1, and F2 are all equal, okay? From this equation, I know N1, I can easily find that N2 is going to be 300, okay? And then I'll simplify this equation, throwing in what I know about N as well, okay? And that'll be 300 x2 equals 150 x1 plus 4.5 f1. Okay, so again, everything above this line is going to hold true for the entire problem. Okay, so now we need to think about what actually happens here. Okay, so there are four individual things that could happen. The top can slip or tip, or the bottom can slip or tip. And we're going to go piece by piece. Now remember, everything above this line, true for all of these conditions. Okay, so let's start with, let's assume the top slips. If the top slips, what happens is that friction force at 1 is at its maximum. That's what causes slipping, which is going to be mu s times n1, okay, which will be for our problem, coefficient of side between the, no, it's going to be the 0.6. So that's going to be 0.6 times N1, which is the 150. From that, I learned that F1, which equals P, then equals 97.5. And again, I don't know if that's the right answer. We'll swing back and figure this out a little bit, okay? So that's one situation, okay? That would be pounds, by the way, okay? So for the top box to slip, he has to push with 97.5. Now, I don't know if that happens. Let's move on to the next situation where the top box tips, okay? And if the top tips, then X1 is going to be 1.5, basically, and moves all the way over to the edge. And if that's the case, then I can take that and plug it into the 150 times 1.5 equals 0.5 times P. And from that, I learned that P equals 450. Okay, that's not happening. Okay, that is bigger than the slipping, right? Again, if you think about slowly increasing your force, it's going to hit 97.5 first. So I'm looking for the smallest P. Okay, so this one's definitely not happening. Okay, now let's go move our attention to the bottom. So let's say the bottom slips. Okay, so if the bottom slips, then F2 is going to be at its maximum. Okay, which F2 at its maximum is actually going to be 0.35, which is the mu s of that, times its N2, which we've determined is 300. It's basically both boxes pushing down on it. Okay, and what we know is that F2 also equals P from above. Okay, and we calculate that to be 105. This also will not happen. 97.5 is smaller than that one. Okay. So at this point, top slip is the most likely, but I got one last one to look at, and that is bottom tips. Basically, the whole thing tips over. And the easiest way to think about this, okay, is let's kind of rethink what's going on. So if the bottom is tipping, this is what the free body diagram looks like. It's going to be one thing with P pushing right here, 300 straight down. It's basically acting as one body here, okay? N is going to be way over here. That is N2, and F2 will be like this. So it's probably easier just to think about it that way, okay? So if that bottom tips, N is going to be over at the corner there, okay? So from this, I can sum the moments, and I'm going to sum it right around this point, Okay, kind of write a new equation here. So I'm going to have that 300, which is going to be 1.5 feet over. Okay, and then I'm going to have the P, which is 5 feet up, acting in the other direction. Okay, and from that, I find that P equals 90 pounds. Okay, which you can see is the smallest one. Therefore, this is the one that is the answer. So again, with friction problems, you're going to have to solve them more than once. The first answer you get may not be the correct answer. And even if it is, you need to go prove it to yourself by either showing that it's less than the maximum, solving it for the other type of impending motion, and that sort of thing, which is the way that friction problems are often done.